The Lambek calculus is a version of linear logic, and it features non-commutativity, and it's intuitionistic by nature. That means that on the right-hand side you have only one formula, and on the left-hand side you have an ordered sequence of formulae. So here it's formulated in a Ganson-style sequent way. So you have two implications, two of them because it's non-commutative, and we have product, which is what they call in linear logic multiplicative conjunction. More algebraically, you can view the Lambek calculus as the axiomatization of the theory of residuated monoids. So you have monoid, you have a partial order on it, and you have these division operations, which are residuals of the multiplication with respect to this partial order. And if you have residuals, it's well known that you do not need to impose, say, monotonicity and stuff like that. It all comes for free. So let's start with a bit of history. Notice a distinctive feature of the original Lambek calculus, which was proposed by Jim Lambek in 1958. And this is the antecedent non-emptiness restriction. So in these rules, well, let's see them here once more. We'll write rules for implication. This pi, the context, was forced to be non-empty. So it's quite a strange restriction from the point of view of a logician, because this means that you cannot, say, derive a formula by itself. You should only derive, say, consequences. But from algebra, it's okay, because you just shift from monoids to semigroups, which possibly are not monoids. And also, it was motivated by linguistic applications. So what does it mean? So, for example, we have this phrase, extremely interesting book. Where book is a noun. Interesting is a modifier for a noun, so it takes a noun on the right and gives us another, say, bigger noun group. And extremely is this an adverb, it's a modifier for the adjective. So if we allow antecedents to be, and this sequent on the first one is derivable, and so this validates extremely interesting book as a valid noun phrase. But also, if you allow the antecedents to be empty, you will validate the second sequent, which corresponds to extremely book, which is ungrammatical. So this means that in, say, natural languages, empty syntactic constructions should be banned, even if they receive some sort of valid type like n over n. And this was the motivation for making this, adding this restriction, but also, of course, the variant of the Lambek calculus without this restriction is considered. And it was also introduced by Lambek, I think, in 1961, when he shifted from, say, these linguistic games to more, say, general logic. And we will denote it by L with lambda on the top. So lambda stands for the empty sequence. Usually it's denoted by L star. I do not like this because for me the star is usually the Kleene star. And in this talk it will appear, so I will use an alternative notation for emptiness. So, and these two systems, they are not directly related one to each other. So say L is not a conservative fragment of L with lambda on top. So they correspond to different classes of algebras and they have different theories. And the theory usually goes in parallel. So if one presents a new result for, say, the original Lambek calculus, then a PhD student can do the same for its variant with empty antecedents and get, say, a formally new result and publish a new paper. But this is not always the case. Sometimes their behavior is different, and in this talk, we'll expose one of these differences. So I was talking a bit about linguistic applications, and they suggest interpreting Lambek formulae as formal languages. But I understand that we're at RAMEX, which is a relational conference. So now I'm shifting to another sort of semantics, which is the semantics on relations, or for short, these models are called R models, as opposed to L models, which are the language models. So this is a formal definition. Of course, it's rather long, but it's understandable. So we have a set W, this support set. We have a universe, so it's a transitive relation, and our relations will be sub-relations of this U. And we have a valuation function which maps formula of the Lambek calculus to relations which are sub-relations of U. And the product is, of course, naturally interpreted as a composition, and transitivity of U guarantees that we do not run out of U. And these are the divisions. So what is it to divide A under B? So it means that if you add something of type A to the left, we'll get something of type B. And this is exactly written down here. And the same for B over A. So it means that if you add something, so if you have something, and you add something to the right afterwards, and that something was of type A, then the result will be of type B. But it's important to notice that all this is relativized to U. So your arrows should still be in U. Otherwise, you can go outside. And for different U's, you will get different models and different truth conditions. And the sequent is true if the left-hand side is a subrelation of the right-hand side. And here, notice that n should be greater than 0. So for empty antecedent, we don't know how to do this because, well, what is the relation for the empty one? So this means that our models, as defined here, they are models for the original Lambek calculus with Lambek's non-emptiness restriction. If we want to go for Lambek's calculus without this restriction, so we extend the calculus, we should make the class of models smaller. And this smaller class of models is called square relational models. So here the universal relation should be just the real universe. So it means that it should be W times W. And in this situation, we can define a truth for a sequent with an empty antecedent also. It means just that the diagonal relation should be included in the relation for B. So the diagonal relation is a natural, say, unit of relational algebra. But today, we will have other units. And these are natural classes of models. So if you have arbitrary models, they're models for L. And if you have square ones, they're models for L lambda. And both are sound and complete in the strong sense, which is a result of Andreka and Mikuláš, 1994, I believe. So here you see that on the left, you have a set of sequence H. And syntactically, you derive a sequence from them. You can use cut. It's not cut-free, and in our formulation, we use the cut. And on the right, you have semantic entailment. So this means that you have an arbitrary R model. And once it validates H, it should also validate the conclusion. So it's the notion of strong completeness. Say in classical logic or in intuitionistic logic, it will be equivalent to the normal completeness because you can just use a deduction theorem. But here, substructural logic don't have a deduction theorem, so therefore this is stronger. And we'll see the examples where weak completeness holds. Weak is for the empty H without any hypothesis, but the strong one doesn't. And for square models, we have the same, but on the left-hand side, you will have this lambda, of course, as a declaration. But the proofs of this stuff are essentially different, and we'll see how this goes. And we'll explore it what happens when we add extra operations. So for the original Lambek calculus, so how do they build, Andreka and Mikuláš, their needed relational model? They construct some sort of oriented graph. They do it in an iterative process. It's quite a long journey, but the idea is that they somehow construct a graph which will going to be our world, W, and our universal relation will be the set of edges of this graph. It will be acyclic, by the way. And edges are marked by formulae or equivalence classes of formulae, elements of the Lindenbaum-Tarski algebra. And then they just interpret this as follows. So you say that the valuation of A is the set of edges such that the label of the edge implies A in our calculus. Or here, you could also add H here. So I didn't put it here, but if you put H before this turnstile, you will get relativized version for strong completeness. This is for weak completeness. Loops are not allowed. In the limit, you will get this universal model. So which means that, so here we should add H, and then it says that a sequent is true there if and only if it is derivable from H. And this follows from the properties of this graph somehow. So for Lambda station is different. So now we're required to have loops for each point because your relation is universal. And a loop should support any formula such that the following is just derivable, of course, right? So because on the loop, you return to the same point, and this should be true. And for example, now we can have P over P or Q over Q. Both say generally true things, but they're incomparable if P and Q are different. And Andreka and Mikuláš suggest using sets of formula as labels. And now, again, you can add H here, but this is for weak completeness. You just take all the, so if for some A prime in this label set, you will have the durability, then you should validate A. So What next? But this still gives strong completeness. The same result, but a different proof. So now let's extend the Lambek calculi with intersection or additive conjunction. So these are the standard rules for them. It's interpreted a set theoretical way, as usual. And we'll denote it like this, depending on whether Lambek's restriction is in. And just a short remark that you could also try to add the union. Union makes completeness fail immediately due to problems with distributivity, so we do not consider that. And in the L case, the proof of Andreka and Mikuláš easily extends to this L with the conjunction, just strongly are complete. And however, for this L lambda, the situation is significantly different. So Mikuláš in 2015, so it's 20 years after that first paper, managed to prove only weak relational completeness. And this is the formulation of that, so no hypothesis. And as noticed before, in this case, our graph gets labeled by set of formulae, not by formulae themselves. And in particular, on this loop, you should include all the formulae of this form. But however, this could violate this condition of intersection, because sometimes you can get A from some A prime, you can get B from some B prime, and they're both their legal labels, but they're not the same. And therefore, A and B will be not validated, but it should be by the rules of the Lambek calculus. If you derive A and you have derived B, you can also derive A and B. But the antecedents here are different. And the solution proposed by Mikuláš is as follows, that instead of arbitrary sets, he considered filters, which are closed under finite meets. And this does the job. But at some point, he uses the fact that there are no hypotheses. Inside the proof, it's hidden, and we'll see how it works now. We propose another approach to that, which uses an explicit unit constant. Now I'll shift to that. So in the Lambek calculus with empty antecedents allowed, well, I said it was the logic for residuated monoids, but it didn't have the unit as an explicit constant. It was implicitly inside. That you could have the empty antecedent, which is a unit on the top level, but you couldn't have the unit inside your formulae. Now we add it with these natural rules, and they reflect the neutrality of the unit, and so the natural interpretation in relations will be, of course, the diagonal. But if you do this interpretation, this leads to incompleteness, and these are examples by Andreka and Mikuláš, by Bushkovsky, and also others. Here you see that these are generally true if you interpret the unit as the diagonal, but they're not derivable in the Lambek calculus due to, say, valence conditions or something like that. And with such extra principles, if we could possibly add them as new axioms, and there's still no clue for completeness because there are many principles, they look different. They use, so one of these uses conjunction, the other uses just divisions. And we don't know how to make the system complete, this first, and also we conjecture that it's undecidable. In the view of analogous results we obtained earlier in the work by Max Kanovich and Andrei Shchedrov in 2020, where we proved undecidability for situational language models, also with the unit explicitly added. Here it's probably also doable. And so we go another way. We want to keep the same calculus as we like it, so the unit is axiomatized just as a neutral element, but we'll sort of a bit loosen the restrictions on the class of models, and we'll consider models with non-standard units. So let A be a subset of the set of all possible relations on W. So which not every relation will be okay. It's not just the set of, it's not just being a subset of universal relation. We just carve out some family of relations, which is closed under Lambek operations and intersections somehow. And this class could have a different unit from delta. So we do not include delta inside, and this could have another unit. And we denote it by 1A. So this is a unit for any relation which is inside this class. And then we do this non-standard model. Just we fix W. Our universal set is still U, W times W. We fix this class of relations, an arbitrary one, but closed under our operations, possibly not including the real unit, which is the diagonal, but it should have this non-standard unit. And we do evaluation function standardly, evaluating the unit as this unit A. And now having the unit, we can actually use the old construction by Andreka and Mikuláš and construct a universal model, and on our graph, all the labels will be just formulae or classes of equivalence of formulae, but not, say, filters or not sets of formulae. Because now we can unify everything which is on this XX by just the unit. And we don't have to incomparable P over P and Q over Q, we just have the unit. And indeed, the set of xy such that this stuff derives one is a non-standard unit. So, and it's possibly an extension of the diagonal relation. So of course, if you have xx, this will be derivable because Lxx is just one. But also there could be other possibilities to get it, and we'll see how it works. But now this will not work with hypothesis, because the crucial part in the construction of the graph is that if we can derive something from the unit, 1 implies B and C, then we can split it and derive that 1 implies B and 1 implies C, which is true in the Lambek calculus itself, and it can be proven easily by cut elimination and proof search. So if you can derive this, you have to remove the unit and you will have just BC, which you have split this operation. Syntactically, it's obvious, but if you have hypothesis, it's just not true, because you can just add this as a conjecture and this will be not there. And an interesting thing is that if you consider redux to the language without the unit and remove all these non-standard stuff, then you will get standard R models. And this means that we have another proof of a more straightforward one for Mikuláš 2015 theorem. But also it's extendable, and we'll see how. It's extendable to infinite conjunctions, because in Mikuláš proof, formally speaking, there were filters closed only under binary or finite conjunctions, finite meets. But here we can also see infinite ones. So I didn't want to develop, say, a formal infinite language in which you have, say, infinite conjunctions of arbitrary, say, countable sets of formulae. And I opted just for one catchy example, which is the cleanest star as a denominator, or so what Igor Sedler called these iterated divisions. So basically speaking, if you have the cleanest star, A star, it's the infinite union. It's 1 or A square or A cube, etc. But if you put it into the denominator, it becomes equivalent to an infinite meet, to an infinite conjunction. And the same for the other side. And so you just add them, and by the same argument, you will also get completeness. And you don't have these problems with the filters being, say, only finite. And so we get weak R completeness for this extension with such operations, just as a corollary of our construction. And now I will end my talk about strong incompleteness. So we have proved weak completeness as Mikuláš did. We extended it to infinite situation. But what about strong completeness? So our proof fails, but it basically doesn't mean that the result fails. But it really fails. And Mikuláš in his paper proposes in a remark a series of potential counterexamples, but doesn't prove that they're really counterexamples. And now I'm going to do some barbarous way. I confess that I couldn't do it algebraically, I did it syntactically. So the first of the examples is as follows. So here, well, you can see that this, you can view this as the unit for simplicity. So here you will have, and D is just added in order to make it not non-empty as in the antecedent. For some reasons, it doesn't really matter. And what happens here, I will just show you the picture. So you have this Y, and you will in Y you will have this, and it says that it implies B product C. So product is composition. It means that you go using B, you go somewhere, and then you go backwards. But let's now look at this intermediate vertex D, Z. On Z, you will have A under A, of course, because it's the unit. Well, it follows from the unit. But also, you will have this inverted thing, C multiplied by B. Because from Z, you can go back to Y and then go to Z. And you can add this inside. And so the problem is that this conjunction, of course, does not distribute over product. This junction does, but conjunction doesn't. So formally speaking, you will have, if it distributes, you would have BC, BC, which is derivable. And also you will have B unit C, so just BC, which is also derivable. But here it's not, because its conjunction is inside. So this reasoning was already done by Mikuláš. Yeah, I was finishing. And but the proof that it's not derivable was not done, and actually it's done in a funny syntactic way. First, we remove A and D by replacing it with the unit. It's fine. And then we just rewrite this axiom, which is now from lambda to BC, as the following against the style sequential rule with concrete variables BC. It's not a rule scheme, it's just your B and C are fixed. And it happens that with this rule, you can eliminate the cut. And then you just do exhaustive proof search and find out that this is not derivable. So we'll have weak completeness, but not strong completeness. And I'll conclude with several further questions. So first, this talk was purely, say, on the semantic side. I didn't think about algorithmic complexity questions, but they're naturally arising. So if you add the unit with extra axioms, which should be correct, will it be undecidable? Probably yes. And also complexity with iterated divisions. So with the clean star itself, it's pi 0, 1 hard. Here we conjecture the same because the power of these iterated divisions is just the same as clean star. So finite axiomatizability for semantic entailment and square error models. So our system is not complete. So there could be principles like this, which should be true, which is right written down here. What is the real axiomatization? It is finite axiomatizable. This was posed by Mikuláš, and we don't know. And also, if we don't have the product, could we restore strong completeness? Well, why? Because our counterexamples heavily depend on the product. And without the product, situation could be easier. So I think that's about all. Thanks for your attention.
Thank you very much. Any questions? Yeah. Thank you for the talk. So the way you upgrade the standard models to the non-standard models by adding the subset A of relations reminds me quite a lot of the transition from Kripke frames in modal logic to generalized descriptive frames, basically to solve similar problems of completeness. Can you comment on anything about this connection?
I think that here it's much smaller example of the same phenomenon because you just cope with not the general, say, problem with completeness, but just with one small constant, which has a pesky behavior. But in general, yes, it's the usual thing you do when you need to fight incompleteness. Okay. So I think this idea was not that new actually, but in relational, so I think they did it in, I think in language models earlier.
Okay, thank you.
Hi, I'm wondering about the interpretation of your non-standard identities. Do you know whether they can always be assumed to be transitive or symmetric?
For transitivity, that should be, I think, the case. I don't know. I didn't try that actually. Mm-hmm. So many of this stuff could come just from the durability of certain principles from the Lambek calculus. Say you have 1 multiplied by 1 implies 1. This should be valid for this unit. Mm-hmm. And actually it's equivalent. So this will mean transitivity. But for symmetry, I don't know how to do this. Yeah. We don't have this. Maybe we'll try. There is a Lambek calculus with reversal. And if you... but I don't know whether to any model you can add reversal. But if you have a reversal, then you will have the principle 1R reversed 1 is the same as 1. Mm-hmm. And this will give you what you need. But here, maybe not. So
yes, that would be quite interesting.
Symmetry will be nice. Yes, thank you.
I have one other question about, you said the complications when you have both intersection and unions. But what if you just have the divisions and union?
No. I didn't emphasize this, but here where we have it, we have the union here. So here, you see, I cite this quite recent paper of ours. It's not this. So if I talk just about distributivity, I would cite, I don't know, maybe Ona and Kamori or someone like that. It's old, say, it was noticed, say, years ago. But here in this paper, we feature a formula which includes only divisions and union, which is a corollary of distributivity, but which is not derivable without it. And this is quite a general result. So this holds for the Lambek calculus in both variants. It holds for commutative linear logic and holds for affine logic also. So I didn't write the example here. It's great. And actually, we used your prover for Kleene algebras to invalidate it for the case of non-commutative, but then we moved to the commutative one and we used the LL prover by Tamura. Of course, in the paper, which is cited in our paper now, it's given a complete proof search independent from any software, which is like 6 pages of proof search. It was so, but when they printed it out in information computation, the font is smaller, so it's like 3 pages. No, this is just with the union. So this exhibits the fact that the union and the intersection being dual, they behave substantially differently.
Still have time for a question, if anybody. I was wondering myself about these iteration operators. Is there any potential role for cyclic proofs? I mean, we've seen some nice cyclic proof systems recently, but for Kleene algebras.
Yes, I like this question very much. So here, as I said, that well, if you have so these are iterated divisions. Of course, you can do just wild Kleene iteration. Well, Sedler introduced them actually in the non-associative case where the global Kleene star is problematic, but this is okay. So, and this is for completeness, you need this. But in general, as I said, there are results on hardness. So with the Kleene star, it's called infinite direction logic. And it's going to be pi01 complete, proved by Bushkovsky and Eva Palka. So what does this mean? This means that your system with circular proofs will be an incomplete fragment. And if you allow cut, then this will reflect some form of inductive principle. And such a system was developed, I think, by Anupam Das and Damian Pous. And this system is useful for proving undecidability of action logic, which I did recently. It was like 2019. But still, it's incomplete, and therefore we do not have a cut-free version. So cut is inevitable, and I think this is sort of a global problem in, say, circular proofs or cyclic proofs, as people call them, for, say, systems of high complexity, because the usual proofs of cut elimination, they go via infinitary proofs. So if you take, say, circular proofs, I don't know, for Gödel-Loeb or for K plus or something like that, you will just have that you consider your cyclic proof as an infinitary one, you transfinitely somehow eliminate the cut, and then you wrap it up back into a circular proof. Here it will not work, and there are counterexamples. That means that you take a circular proof which cuts, you unravel it, you eliminate the cut, it's no longer circular. And so the same happens in arithmetic, like I think, who was it? Alex Simpson did it for, so he did circular arithmetic, which is equivalent to piano arithmetic, but again, the cut is not eliminable. And this is sort of a phenomenon, I think, of very general nature, and we don't know what to do with that, actually, because we don't know how to. Maybe we could consider some more general proofs which are regular in a more, say, higher level sense. It's not circular, but you have some evolving pattern. So here, usually you have this, that you have A, then A. So each iteration of your proof, it's not the same cycle, it's not the same copy, but it's somehow generated maybe by some sort of Behe automaton or something like that. But it's a very good field of future research. But now, even now, the circular proofs, they help proving algorithmic results. So my proof of undecidability was based on modeling circular behavior of Turing and Minsky machines in circular proofs, even with cuts. So this is sort of a counter-argument to Gérard's claim that a proof system without cut elimination is like a car without an engine.
Thanks a lot for this wonderfully detailed and somewhat conclusive answer as well. We have to move on, so let's thank Stepan again.